Okay, let's get started then. Oh, okay. So here's a link to the slides. I recommend if you have a laptop, take it out right now and please open the slides up on your laptop as well. It'll help you follow along because we're going to go a little bit quick because we're just going to be covering some basic concepts and then we'll be doing like a coding exercise at the end. So that's why we try to get everything done on time. And also, please fill out this attendance form. Everyone needs to fill out this attendance form, actually, including me, because this is how we get our food. You fill it out. Okay. Okay. All right. Does everyone have a link to the slides? Oh yeah, just take a picture or whatever.
So thank you all for pulling up. Just out of curiosity, what is your programming experience like? Have you taken? So raise your hand if you've taken like a first class in CS, like CSE 11 or ECE 15 or something like that. Okay, good majority. Raise your hand if you've done like a bit more than that. So you've completed like lower div courses in CS or familiar. Okay, also a decent chunk. Okay, so I think we can go maybe fairly quickly through the sort of basic stuff, and we can get to the actually interesting stuff.
Okay. So first of all, you're gonna need to, you have two options. You can either install Rust on your computer if you want to use it later, or these links might be a bit small.
You can use the Rust Playground.
Yeah, you can also use Rust Playground.
So you can just Google that Rust Playground, or that's at play.rustlang.org. Or you can just go ahead and install it. If you're on Linux, you can just go to the Rust website. There's a thing there's a command it'll give you. Or on Windows, yes.
Can you quickly fill up or take a picture of that slide? You just came in, so take a picture. You need to fill out this attendance form, and yeah, that will take you to the slides. All right, cool. Okay, yeah. So you guys have the options. I would also recommend taking a picture of this. If you already have the slides on your laptop. If you have the slides on your laptop, try to pull up the slides on your laptop so you can kind of follow these links. It'll make it easier than having to type them out. But yeah, essentially, while you're installing, Rita Bond and I are just going to be talking a bit about Rust and systems programming. Okay, so I'll start by kind of going to systems programming. So systems programming is like a very important concept in computer science and in our modern world especially. So essentially what systems programming is, it's programming with like hardware as a focus. So particularly using your hardware resources efficiently. So this is incredibly important in a variety of like applications where you might need to do this. For example, like real-time use cases, also like performance critical, like scientific computing, for example, or typically resource constrained applications. So one example is embedded systems, where you have very little resources since you're using a tiny microcontroller with not a lot of RAM and not a lot of compute. And you also want power efficiency typically. So these systems are typically seen in like robots, IoT devices, computer networks, even like radio and telecommunication devices. And essentially systems programming is very important since we're writing very efficient code that uses a very little compute necessary, since we don't have much compute available. And then in distributed systems, there's another case where distributed systems we're trying to scale very large, and we want to maximize our performance since we're going to be running a very large and compute-heavy application. So for example, GPU clusters for machine learning, video game servers, or financial systems. Rita Bond's going to tell you a bit more about why we use Rust.
Why the hell would you use Rust for this? But out of curiosity, how many of you had heard of Rust before showing up today? Most of you, wonderful. So sort of this is my propaganda slide. The reason you care about Rust is that it's really fast. It's as fast as C++. It compiles down to assembly in the same way, using the same LLVM optimization that Clang does. It's reliable. This is like the thing that has made Rust so widely used is that it takes this whole class of memory vulnerabilities, things like null pointer exceptions or buffer overflows or use after freeze or double freeze, or all of these errors that I'm sure if you've ever taken like a C class you have dealt with, Rust kills them at compile time. Code will not compile if there's a memory safety issue. But it's also a really modern language, and I hope to show off some of these features to you today. It has really nice package management. It has iterators, enums, traits, async, and a lot of people are using it. Like the Linux kernel has started to use it. Google recently announced that they've rewritten a substantial portion of Android in it, and their memory safety vulnerabilities have plummeted. Microsoft and Google both say that like 70% of their bugs emerge from these memory safety issues. So you're sort of getting rid of this enormous class of bugs. Even the military is getting in on it now. DARPA has allocated like several $1 million on rewriting enormous swaths of military code in Rust. So yeah, it's very exciting. It's an up and coming language, and there's absolutely a lot of uses for it. So hopefully you got started with a little bit of you got started installing it. If you have your laptop open and the basic installation worked out, then you can just it's very easy to get started. You pull up a terminal, type in cargo new, and then if you run it, you will get a Hello World application. Do folks want to do that? Should I give you like half a minute to run cargo new?
People are just coming in, so I'm writing the link to our slides on the board. Actually, you just want to quickly go back to the QR code so that you can picture the slide.
Sure, if you just came in. Yeah, if you just came in, you can grab a slide.
Please take a picture of those slides in the attendance form.
Yeah,
you should put the link to the Bitly as well.
Yeah. Okay. So let's run through some basic Rust really quickly. Most of you have probably seen these in other languages before, so this should just be syntax for you. In Rust, you declare variables with let. You don't have to specify the type, but it is a statically typed language in that types are known at compile time. You can define a mutable variable. Let defines variables that cannot be changed. If you want a variable that can be changed, you have to use this mute keyword. And you will see that this distinction between mutability and not mutability is really important in Rust. And you can also use the const keyword. This is kind of like const expert if you use C++. It's a constant that's baked in at compile time. This is kind of a cute feature in Rust. It's called shadowing. If you have a variable called x, and then in another scope, you create another variable called x, it shadows the outer variable. That's different from saying that x has been modified. What it's actually doing is that the x in this internal scope is just hiding the variable from outside. Data types. So I said you don't have to specify the data type when you declare a variable. The answer is you can, and you can do this with this colon syntax. And Rust more or less has the data types you want a low-level programming language too. You have all the integers, and you use a notation IH for I bit size for signed integers, U for unsigned integers, and you have booleans, you have characters. You have strings. Strings are complicated. Ask me about them later if you want to know more about the strings. But yeah, you have floats, and yes, you have tuples, which are just combinations of data types. So you just use parentheses for them. Very, very easy. If you use Python, it's exactly the same. But you access elements with something funny happened there with this funny dot notation. You use like dot zero.
Yeah. Oh, wait, you want to All right, as you can see here, in this tuple declaration, we're declaring like in the parentheses, we declare the types of all the elements. So we have like 32-bit integer, we have 64-bit float, and then an unsigned 8-bit integer byte. And then those are like the 3 values. And then destructuring, like again, Udebon mentioned, like is an operator. Destructuring is also another way. So in this case, we do let x, y, z equals 2. X is assigned the value of 500, y is assigned the value of 6.4, and z is assigned the value 1. And then you can later use those variables in your program.
You can make it.
Oh, yeah. Okay. Another basic data type are arrays. So arrays can hold like multiple values, like tuple. But the thing with arrays is that all the values have to be the same type. Where in tuples, there can be different types. And arrays are typically fixed length and statically allocated on your stack. So they're best used when you know the number of elements. If you don't know the number of elements and you want to dynamically allocate on the heap, you'll use a vector, which I guess we'll get to later. yeah, I guess this is kind of examples of array declaration. So like the first one's kind of one you might have seen before, where you just have like let A equals 1, 2, 3, 4, 5. Another one is where you declare the type of the values, and then you say the length of the array. So these are 32-bit signed integers. And then the third one is where you have 3 colon 5. So this is a bit confusing, but essentially the first value, so this is when you want to have an array of all the same value. So the first value is the value of your elements. So, and then the second is the number of elements. So in this case, we're creating an array of five values, and all the values are 3. So it's basically an array of 5 threes. And then, yeah, accessing array,
yeah.
Accessing an array element, we just use brackets like other
languages. Functions also are not so different from other languages. The keyword here is fn. And I guess the one minor thing to note is that if you have arguments, the types of the arguments, which you do need to specify, they are not inferred, go with a colon afterwards. And if you have a return type, you would write afterwards with an arrow, like dash greater than symbol, and then you would put the return type. But yeah, functions more or less work the way you expect them to. We'll talk about some subtleties with how arguments are passed when we get to the borrow checker. But you should, but yeah, function. Oh, here we go. This is what I was saying about return types. It's use a little arrow, and functions are sort of scoped in the way you expect them to.
And yeah, this is just kind of showing if else or if else if and else in Rust. So it's pretty similar to other languages, except you notice that you don't need parentheses, kind of like Python.
Yeah.
But so it's kind of like combining a little bit of Python syntax and a little bit of C++ syntax. You don't need parentheses, but the rest is basically the same as C++ and C.
Yeah.
And then yeah, these are just like the 3 different types of loops in Rust. So we have like while loops and for loops. In that case, the first one's basically like a for each loop, like for element in A. If you've seen a for each loop before. So for every element in your array, you're just kind of iterating over each element and print them out. The second one is using a range. So if you've used Python before, you do like for I in range, you basically have for number in 1 through 4. And then, yeah, we also have the loop statement in Rust. We want like, what's kind of the difference?
So loop by itself is an infinite loop. It just keeps running indefinitely. But you can use this funny tick notation. And what this says is that this scope has a label. And then when in the break statement, you can sort of break out of the loop that you choose to. It's kind of cute, I guess. But as cool as loops are, I think the first Rust feature that's like not probably something you haven't seen before, or maybe something, I don't know, I shouldn't presume, are iterators. So, you can write code using a for loop. You can iterate through and say if something. But one of the really cool things about Rust is you can write things in this functional style where you say, I have a vector v, I want to iter over it. So this is giving me an object that's an iterator. And then you're going to call functions like filter, and you're going to pass a function into filter. So the into filter is being passed an anonymous function that takes in an I and returns the Boolean I mod 2 equals 0. And so this will only keep the elements in the array that are even. And then for each one, we map it. So we're performing this I times I operation on each element of the iterator. And we're taking this whole iterator and collecting it up into a vector. So these anonymous functions in Rust are closures. One of the reasons you might want to use an iterator is that it's usually more efficient. The Rust devs have put an enormous amount of effort into making sure iterators compile down as efficiently as a raw for loop. And they can be more efficient at times because if you're indexing into an array, the iterator will avoid bounds checks. And also, iterators are lazy. This is kind of a subtle point. Until this collect function is called, the iterator does nothing. You should just think of it as the operation you're describing has been like built up into an object. And then once you call collect, it actually like pulls through the iterator. It pulls the objects through the iterator and collects them all together. But you could do something else. You could do sum, and that wouldn't even allocate a vector. It would just pull each element through and add it up to a running total. Or you could do product, or you could just take the first n elements, or you could skip every other element, and it would just pull the elements through as necessary. Under the hood, the way this works, and this is maybe a little bit of an expert thing, if you've seen these ideas before, is that iterator is what's called a trait. And this is one of Rust's like stellar features. A trait is the way that Rust builds abstraction. And the idea is a trait is like it's kind of like an interface in Java, if you've seen that before. It's a thing that a type can implement. You say a trait, something is an iterator if it gives me a function next. Next being a function that takes in the iterator and gives you back optionally an item. An item being just some type associated with the iterator. So lots and lots of different types can implement iterator. And what's cool is that the Rust gendered library literally provides you dozens and dozens of methods for iterators. We're saying, as long as you give me a type that implements next, then you get access to all of these methods and you can chain them together like this. You can do filters, you can do maps, you can get chunks, like you can get chunks of elements, you can get windows, you can get all of these really cool functions, and all you have to do to get it is implement next on your type. Okay. So
basically, another basic concept of Rust. If you've done C or C++ programming before, structs. So essentially, even if you've done Java before, think of struct as basically a very simplified class. So in a struct, instead of like a class where you have public and private kind of scopes, in a struct, everything is public. So that's basically the difference. A struct is basically kind of like a building block of what becomes a class. We just have, so a struct, essentially in a struct, you define a bunch of fields. They can all be different types, like a tuple. So you can have, like, for example, a bool field, you can have a string field, or like unsigned 64-bit. And then so once you define your struct, then you can create instances of your struct, kind of the way you create class instances. So you can kind of see here in the main function, we're creating an instance of our user struct called user1, and we're giving it some values. So we're setting active to true, setting the username to some username 123, and we're sending email. You can do this, and this is called what's called a builder pattern. You can also do at the bottom where you just assign each field individually using a dot operator. So you could just do like let user1 equals user colon, and then you could just assign fields one by one. And then you can kind of see at the top there, we also have what is like a function where you can use a function to build a struct. So it kind of does the same thing as you can kind of see in the main function. Except in this, you can create many instances. And the way it would work is you would just, this user is actually a return. So we'll kind of cover later, but in the method section, but essentially, the way Rust does it, we don't use the return keyword. We just use, essentially, when you want to return a value, you don't have a semicolon. So this user is actually a instance that gets returned from the build user function. So when you want to create new instances, you could just do let user1 equals build user, and then pass those parameters to that function. And then you can let user2 equals build user, let user3 equals build user, etc. And then one final way of initializing structs instances is if your struct instances share a lot of their values of their fields in common, you can just assign manually the fields that are different. For example, right here, the user2 has a different email from user1, so we assign that manually. But the rest of the fields are the same as user1. So active is true, the username is true, but it's the same, and sign account's the same. So when we want to copy all those fields over, it's very simple. If you want to copy it, just use ... and then the name of the instance you're copying from. So in that case, we have ... user1, and that automatically copies anything else from user1 into user2. And then, okay, so methods are basically like functions, but they're declared within the context of a struct or enum. And their first parameter is always self. So have you used Python before? Oh, question?
Yeah, I wanted to ask. I know you said strings are complicated, and I know there's many types of strings. Rust, as a friend of ours, but if it's set at compile time and you're switching some strings later for structs, you have to worry about things that are not saved on the stack.
Strings are complicated. Talk to me afterwards, Paco. You know what you're doing.
Okay. Anyway, the methods are basically like functions, but for structs. So like I was saying before, right? How a class is essentially a smarter version of a struct. That's because basically classes are structs, and C++ classes are built on structs. So like, yeah, class is just more advanced version of structs. And we can see that because we can even give structs methods, even in C++ and in Rust. So in Rust, the way we do it is we use a block called impl, so impl, that keyword. And we just, so if our struct is named rectangle, we create an impl block named rectangle. So that'll now assign methods to our struct. And then we put all of the methods or functions for our struct inside of that impl block. So we right now have only one method, but we can have as many as we want. So we have like the area method, which basically takes in the self. So when you create an instance of a struct, each instance will have its own unique values. And that's why we use self, because self is not using, it's like kind of like, if you use the static keyword in Java, where static is like for all instances, this is for that specific instance. So this is for the specific instance of your struct. So it'll take that instance's width, it'll take that instance's height, and it'll calculate the area. So in this case, our instance rect1 has a width of 30 and a height of 50. So that println statement essentially prints out the value 1500.
So enums are another one of these like very cool features in Rust. You might have heard they're a bit different from enums in other languages in that enums in Rust can have associated data. So you can imagine, so the enums in most languages are just like a thing that can take on a finite number of values, and it's kind of boring. It's like, okay, we have an IP address kind. It can be either version 4 or version 6, and you just index the two types, but with this like double colon operator. But in Rust, you can also have enums that have data associated with them. So enums are basically as powerful as structs. So here you can have v4 with 4 U8s associated with it, or v6 with a string associated with it. And depending on which variant, and so you can create an object that is like the enum in version 4, or you can create an object that's the enum in version 6. And this is a type that sort of is, whose values can either be in this state or in that state. And this can be really powerful. For example, there's this really cool type called option. Rust doesn't have null and because nulls are terrible. Null pointers are terrible. What you have instead is this enum called option that is either a none or it has a variant sum that has some data associated with it. And if you want to have a type that can be null, you just say that that type is an option of whatever type you want. And then you can treat it as an enum and sort of do all the usual things with it. And you can write like sum 5 or option something is equal to null.
Notice that T, oh yeah, just want to interrupt that. Notice that T in the option, if you've not covered generics at programming class before, maybe
T could be anything. Like we're just saying T is a type.
Yeah.
It could, but when you instantiate a particular enum, like option I32, this I32 gets substituted for the T. And this is actually implemented at compile time. It's very clever. It's called monomorphization.
Basically, like if you cover generics in Java or templates in C++, it's the same.
Templates in C++ are stupider, but that's a different rant. Because they just expand out and they do the type checking after they expand out instead of doing it before. So one of the nice things about enums is that you can do matches with them. This is sort of the bread and butter of how to work with enums, and it's kind of like a switch statement. But what it does is it takes in some type that you pass in some type that's an enum, and you can match against all the possible values. And within the match, you will notice you can actually like destructure the enum. So this is very similar to the destructuring the tuples that we saw earlier. You can destructure any data inside the enum right in the match statement. It'll pattern match the value against the pattern that you've given, and it will run the code that's like after these arrows, which is kind of cool. It ends up being like really quite powerful in a lot of situations. If-let is kind of another way of doing a match when you only care about one case. So you can write if. It's kind of strange syntax, but what you should read this is if this let up works. So if you can take the coin and match it to coin quarter state, then you're going to run this code. Otherwise, you're going to run this code. And the state variable is accessible inside of this if scope. Okay, so if-lets, they don't let you do anything different from a match, but it's somewhat nicer syntax that's useful occasionally. Okay, and we're on to borrow checking. Any questions about what we've done so far? We've kind of gone through like the bread and butter of things that are not so different from what you've seen in other languages, hopefully. Are we feeling okay about this? Bar checking is more interesting. Bar checking is what it lets Rust solve all of the memory safety issues in C++ and other similar languages. And the canonical example to look at is, say I have a vector. Say I have a vector v. One thing you could do is you could iterate over the vector, and inside of that, you could push to the vector. And you might think this is perfectly reasonable. This looks like okay code that you could write in many languages. The problem is that every time you push to v, it's a vector, so there's a chance the entire vector gets reallocated somewhere else. So that means that this I, which is a pointer to inside of the vector, can get invalidated. And this is a very fundamental issue. Like this looks like a bit of a contrived example, but you can imagine that instead of a vector v, this could have been an option. And we took a reference to the thing inside the option, and we handed it off to someone. We handed it off to some like manager class, and that manager class like lived forever. And then somewhere else in our code, we set that option to be none. That would be a problem because now that manager class has a reference to an object that no longer exists because we set it to none. So this issue is very fundamental. And the way Rust solves it is by very strictly enforcing a rule. The rule is that you can either have many immutable references or you can have a single mutable reference. What I mean by that is that when you create a reference in Rust, you use an ampersand symbol. If you use just the ampersand symbol by itself, it'll be an immutable reference. If you write ampersand mute, then it'll be a mutable reference. And immutable references only let you read data. Mutable references let you read or write to it. And the Rust compiler is very, very good at, and this is a rule that will be enforced by the compiler. Rust is very, very careful to make sure that this can be checked within each function, and the compiler will yell at you if you violate it. Like in this example, it'll tell you in very clear language that you cannot borrow v as mutable because it is also borrowed as immutable. It'll underline that the immutable borrow occurs in this iter call, and that the mutable borrow occurs when we call push. And if you look at the documentation for iter and push, you will see that v.iter, it takes in a reference to v. It's written like the ref self, and v.push takes in a mutable reference to v. And so as soon as you call these two functions, you've created a simultaneous immutable and mutable borrow, and the compiler will yell at you. And this is really unintuitive. Like if you've grown up programming like I have in like languages like C# and Java, where the standard paradigm is everything has a reference to everything, this takes a long time to get used to. But once you get used to it, you realize that it solves everything. Like as soon this solves all of the memory safety issues, because it means that at no point do you have no point can you see something that might get pulled out from under your feet, and that ends up being really quite powerful. There's some syntactic subtleties that you need to use to make sure, and maybe we'll talk about them. But yeah, do you feel okay about the idea of immutability versus mutability? That you can either have immutable references or just one mutable reference, but never both at the same time. Sometimes these are called shared references versus exclusive references to highlight that. Yeah, what's up? What do you mean exactly? Rewrite this code. Yeah. I could. Well, the problem is that it's not entirely clear what this code actually should be doing. Like part of the reason the compiler is yelling at you here is because this code is actually kind of nonsense. Because if you imagine you have this array, you're iterating through it, and every time you try to do something, and every time you hit an element, you take a copy of the element and push it to the end of the array. So it would be it's actually causing an infinite loop as well there. But you can imagine what the right thing to do if you need to mutate v while iterating over it is to actually call v.iterMute, and this will give you a mutable reference to the thing inside v, to the element of v, and now you have a mutable reference just to that one element. So you can modify that one element inside the for loop. Okay, but Suppose you need to do something a little bit more sophisticated, like you needed to look at neighboring elements as well. Then there are iterator functions that you can use to do that. There's one called windows. So you could do like .itermute.windows. And what this would do is it would give you windows of a certain size, and each one of them would be mutable. The point is that this is actually like, it is actually like, part of the reason it takes a while to get used to it is there's no like silver bullet solution to go, the compiler's yelling at me, fix my code. You kind of just have to get the reason the compiler is yelling at you is that your code is wrong, is genuinely wrong. And that takes some time to get used to. But it's a really cool idea. It's a really powerful idea. Like this is what makes, if you look at the Google blog that I showed you earlier, they have this great graph where they show that in C++, the number of memory vulnerabilities is 70%. And they just have this graph that goes dum, 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 as they rewrote parts of the code in Rust. This is why that happens. This is why those bugs just vanish. So let's talk about something lighter, because memory safety is complicated and it'll take you a while to get used to. One of the wonderful things about Rust is package management is easy. If you ever use C, package management is hell. You have header files, you have translation units, you have a linker, you have to include them, you sometimes have shared libraries, you have DLLs. It's such a pain. Rust makes it as easy as imaginable. All you do is you have a cargo.toml file, and instead that you add a line that gives your package name equals version. And if you want to do something fancier, you can also do something like this. In parentheses, where you say version is equal to something, and then you can ask for features. And you just put this in your file and you run cargo run, and it will just grab the packages for you. And it works.
If you've used Java before, you've used the build.gradle file, or it's kind of similar to that, like basically similar to Gradle.
Yeah. Or it's not so different from like the requirements.txt in Python, but I think, by the way, this library that I'm importing, Surd, it's genuinely so cool. Like, I don't know, do you guys know what serialization versus deserialization are? Okay, what I mean by serialization is I have some data in my program, I need to convert it to a string, either to like send over a network or to store in a database or store in a file or something like that. And normally when people write this, they often hand roll their own code. They'll just like write some code that converts their type to a string and then they'll like send it over the network or something, or do something silly like that. In Rust, and I've like worked with C++ libraries where there are literally hundreds of lines dedicated to hand rolling your own serialization. In Rust, there's this wonderful library called Surd, and you add one line, you like derive, serialize, deserialize, and derive, what that means is it'll automatically implement a trait for you. And then serialization is one line. Like you write surd JSON.toString, and it will just take your thing and it will convert it to JSON. And you can do the opposite, and you can do it for a million different formats like JSON, YAML, TOML, whatever you want. Just works. It's so.
By the way, that top statement right there, use Surd, is basically like the equivalent of the import statement.
Yeah.
Or like the include statement.
Yep. Okay. Hands-on portion, because this is fun. What we've set up for you is some skeleton code to that, and the goal is for you to implement a Lorentz attractor. You're getting to do this because I'm kind of a math person and I'm kind of a math person and a graphics person and I enjoy things like this. But yeah, if you head to that link or you scan this QR code, you will find yourself on a GitHub page. Oh no, is it Lorentz with a T? It'll be really embarrassing if I don't know how to spell. Yeah, okay, the answer is I don't know how to spell. It's Lorentz with a T. If you go, but yeah, if you head over here, we've written up some instructions for you, and the goal is for you to try that. Should they get pizza if they want now?
Yeah. Also, does anyone have any questions?
Yeah.
Because we kind of went through a lot. I hope you all have the slides to play with,
Yeah.
because that's kind of the point. You guys could follow along the slides you place. Also, if you want more information on Rust, I highly recommend checking out the Rust programming book. We'll link it on one of the first few slides. Because that book has amazing, really nice, well-written tutorials to follow through and learn Rust. I looked at the book myself. I honestly, when I was making this presentation, I didn't know Rust really much before it. So yeah,
Yes.
I highly recommend the book. It's much better than most other documentation I've read. So.
Yes, the Rust book is wonderful. In general, Rust documentation is very, very good. In particular, oh, sorry. Let me just pull up a new tab. Oh, no. Let me just pull up a new window. If you go to just search for the Rust standard library, you will find that Rust has this wonderful thing called docsrs and nearly every Rust library is documented in this format. If you search for any Rust library on the Rust libraries website, crates.io, so if I search for like CERD, you will see that these libraries all also have documentation on the same docsrs site, and it's all formatted very nicely. It's very easy to make your own documentation. You just literally type in cargo doc, and it will make you a page like this based off of your doc comments. But yeah, for the hands-on portion, head over to this website. We've written up some instructions for you, and we will sort of go around and help and sort of check in on how you guys are doing and help you out and discuss anything you might have questions on. And if you want, feel free to grab pizza in the back.
Yeah.
Yeah.
Questions? Does anyone have any questions right now? Or
what's up?
Oh, yeah,
Ooh.
that's called a macro. So
Yes.
Macros.
Yeah. So it's not something that's worth thinking too much about. But you notice that like println has an exclamation mark after it. It's because println is a macro. The way to think about this is that println can take in arbitrary numbers of arguments. Like you could have like parentheses, and it can take in like a bunch of arguments to format into the string. So it can't be a function. Rust doesn't allow you to have functions with different numbers of arguments. So println is a macro, and all that really means is it substitutes in some code for it. Yeah. So the way you write macros is you use the syntax. It's kind of funny syntax where you write like macro rules exclamation mark, and there's some syntax for it. But yeah, it's not an important. It's not very.
C and C++ also have macros. I think you use like the
hash define is similar. Rust macros are more hygienic in the sense that hash define is literally like copy pasting code. Like it'll just like take whatever you write and substitute it in. Rust macros do the substitution at the level of the abstract syntax tree. So scopes are basically handled the way you want them to be. But yeah. Okay.
Taking a break. Has everyone filled out the attendance form, by the way?
Oh yeah.
That's very important in making sure that we get our food for our events. So please fill it out if you haven't already.
Hello, people. Yeah. Amazing.
Hey, do you know how much your content is on a daily basis?
Oh wait, we used to. Oh, Ridwan, did you stop recording? Let's see. Stop recording. Stop recording.